So far we've only seen linear equations pop up, quadratics, but other functions can model things in the business world or real world. So we're just going to briefly review some of these that you've seen in your previous courses. So we're going to start with some of the parent functions. You know, the special parent function for linear functions is y equals x. It's a perfect line. It's also called the identity function because every x value equals its y value and so forth. And a special linear function is called a constant function when y equals a number. And so that's a constant function because it never changes. We also have what are called power functions. And that's when you have x to some power, like x squared, x cubed. Even a square root could be a power function because that's technically x to the 1/2. These are also, some of these are also are polynomials. X squared, x cubed, x to the 4th are considered polynomials. But in this class, we're going to mainly be dealing with how to graph them using the calculator, understanding some basic movement of them, and that type of thing. So let's go ahead and look at the movement of graphs. So let's remember some things. If we have a function and we do something on the inside, add or subtract on the inside with the x, that's going to shift, the graph will be shifted h units in the x direction. It's going to shift us in the x horizontally. And the k is going to affect the y direction. It moves us up or down. So a lot of this we can see using a calculator. Some of it you may remember from Algebra 2. So here's the parent function of y equals x cubed. So I'm going to go in my calculator, and that's x cubed. And that was a regular window, so I'm going to go back to the standard window. Remember, you can do all this in Desmos as well. And what's going to happen when I change that to -3 at the end? Well, that's the k, so it's going to affect that vertical direction. And I hope some of you remember what it's going to do. But if you don't, we're going to investigate it here. That moved it down 3 units. What about when I do something on the inside with the x? So x minus 2 cubed. A lot of people think that's going to move left. Here's my original. It actually moves it right 2. If it had been a plus inside, it's actually going to move it left. So what's going to happen if I combine them? Well, it's still going to move it right 2, and the -3 at the end. So here's my original. Here it is. So it's still moved right 2, but it's also got the down 3. So you can combine those transformations. Now polynomials, that's the x squared, x cubed, x to the 4th, that type of thing. In Algebra 2, you learned about the behaviors. Since we're going to be doing a lot with the calculator, I'm not so concerned with you memorizing those, but it is good to know what they look like. So an x to the 4th is even degree, so it's going to behave more like an x squared. So let me look at what that looks like on the calculator. Let's look at that graph. Here's the main 10 by 10 window, just like I have Okay, so we see that it behaves kind of like a quadratic, but it's doing something interesting right in here. So I'm going to kind of zoom in a little bit. And you can actually press zoom in, and notice how it's right at the origin. I'm going to press zoom in, and let's see if I can see it a little bit better. So we have these turning points. It's turning 1, 2, 3 times. I can see that it's crossing the x-axis at -1. It's hitting at 0, and then it's turning around again at 1. So I've got this behavior of it doing this, this, and this. So I'm not getting exact on this. I just want you to see that behavior. And know that you want to kind of zoom in when you want to see more. Rational functions pop up a lot too. Now this rational function just means we have a fraction and there's a variable in the denominator. With these, we can use a table to help us graph it. So I'm going to actually make a table. And if we want to go -5 all the way to 5, I might need to move over here, and well, that's fine. I'll just do it here. X and our Y values, and we've got -5. And I'm going to write them down, but if you were doing this on a homework or a test, you could just use the calculator to copy them down. So Y equals, this one's going to be more helpful to use, like I said, a table, and we'll get some of the ideas on it. Oops, I forgot the x. 3x minus 9. Hit graph. Whoop. So, I'm zoomed in a lot. Let me zoom back out. Let's look at the graph for a second just to get a feel for what it looks like. But I hit, I'm too zoomed in. So this is a rational function. It has like 2 branches on it, and they're kind of split. This one's going this way, this one's going this way. So the table's going to help me get some more points to plot. So I'm going to go second graph, and that goes to my table. And it is not giving me my decimals. So I'm going to go to mode and change this to be decimal. Right now it's on auto because I really want decimals to graph because it's a lot easier to graph. So this is 2.1, basically 7. This is basically 1.9, 1.6, 1.1, 0.3, -0.9, because we really don't need to go too many decimal places if we're graphing. -10.7, and this says error. Which is kind of weird. We've got an error there. And I want to kind of play with this a little bit. If I keep going left, notice that the numbers aren't changing that much. 1.1, 1.6, 1.9, 2.17. As I keep going into the x values, notice that they're leveling off. It looks like at 3.6. I know it's leveling off even further. 3.7. 3.8. It actually levels off at 4. And you might be able to see it better if on the graph if we hit trace and then we keep going that way forever and ever and ever. It's leveling off at 4. And that's actually because if I look at so as my x's get really, 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 really big, it doesn't matter what the numbers at the end do. If I took 12x divided by 3x, it'd be at a 4. So there's this like horizontal asymptote at 4. That's not too important right now. I just like to fill in. So we got a 2. This is like a little less than 2. It's about halfway, a little over. And at 1, it's at 0.3. And 0 is at like negative, then negative 3. And then all of a sudden it jumps down to negative 10. Then the other side is way up at 18. Like, way up here. And then, oops, I was in the wrong spot. Oh, at 4, it's at 18. And then at 5, it's at 11. And I wonder what happens as I keep going. So I'm going to go on the other side of my graph with my trace. So we stopped at 5. Oh, that was a good number. Where was that at? Like 6.5. We're at 8. And then I wonder what it's going to do as I keep going this way. It's actually going to level off at 4 that way as well. So I end up with this graph that does something like this. And one of the things about these graphs is we actually do have what is called a vertical asymptote, separation this way, and it's easy to spot because it's when we have an error. It's called a vertical asymptote. And the reason we have an error there, or a vertical asymptote there, is if I plugged in 3 times 3 is 9, 9 minus 9 is 0, and remember we can't divide by 0, so it actually sends this graph into crazy world. There's also a horizontal asymptote, and we'll discover more about that later, but it's actually at y equals 4. But we're just trying to get the idea of what the graphs look like. So any rational function is going to have this interesting system of asymptotes, of boundaries, because it's two pieces of a graph. All right. And we can actually see how that gets used in this next example. Suppose we have this as our total cost function, and we want to look at the average cost function. So average cost. So this is the total cost. So I want to think about average cost. So that would be, so average cost is represented by this symbol. That would be if I took my total cost divided by the number of units. That would be the cost per unit, or the average cost per unit. So that would mean I would take that 900 plus 3x plus x squared and divide that by x. And let's get an idea what that one looks like. I may really have to play with my window on this one. So 900 plus 3x plus x squared over x. Now, I'm going to go ahead and hit window where we were kind of at. But I want you to think about why I'm not seeing anything. This is not fitting in my window. Remember, we talked about that. We're going to have to play with the window a little bit. So, do I really care about products in the negative region? Not really. So I'm going to change my window, and I can start with like a -1, but I'm going to go all the way to like, let's try 100. And my y values, cost is not going to be well, it could be negative if you're losing money. And we'll try it like 100 there too. Let's just try that. And notice I'm seeing one part of those branches. that's because the other part is over in the negative world. So we don't really want to worry about that. We want to determine, so let's sketch this real quick. We have our window here, and the graph looks something like this. And we want to determine the minimum average cost. So we're trying to find this value right here. Well, this isn't a quadratic, so I can't use the shortcut of finding the vertex. But we can find the minimum value. Just to let you know, on Desmos, you can kind of play with the points there. I could even hit trace and just kind of guess. But on a graphing calculator, there's actually a way to do it really easily, and it's under calculate. C-A-L-C. So I'm going to press second and then the trace button to get to the calculate menu. And there's an option that says minimum. Left bound means you want to be really to the left of where you think it is. Press enter. Right bound means go to the right of it. What we're doing is narrowing down the calculator to find that point. So we're saying look between these two lines. And you press enter, and it says the minimum is at 29.9999999. That's basically 30, comma 63. So what that's telling me is that when we have 30 units, the average cost is at a minimum of $63 per unit. Why would a company want to minimize their costs? Well, so they'd make more money. All right, the last special type of function we're going to look at is called piecewise functions. These occur a lot in the real world. So let's just use this example. So the 2012 monthly charge in dollars for kilowatt hours of electricity used by residential customers in this corporation is given by this function. So they calculate the monthly charge differently if you use between 0 and 100 kilowatt hours than they do if you use 100 to 500. And then they calculate your charges differently if you use over 500 kilowatt hours a month. This also happens like when you have like cell phone plans sometimes, that if you use this many data usage, this is your plan. If you use this much, this is your plan. So it's similar to that. So what is the monthly charge if 1,100 kilowatt hours of electricity are consumed? So which rule would I be following if the customer is using that much kilowatt hours? Well, that's over 500, so we'd be following this rule, that third one, if X is greater than 500. So we would have to, so C of 1,100, we're going to plug into that third option. So they're charging me a different amount because I'm using more electricity. So 67.9 plus 0.119 parentheses 1,100 minus 500 gives me, and remember this is money, so this would be $139.30. When it's money, you always do 2 decimal places. What about if we used 450? So which rule would we follow to charge a customer if they used 450? Well, we'd use the middle one. So we would type in 22.70 plus 0.113, and then 450 minus 100. Notice if I'm typing it in the calculator, or if you're typing it into Desmos, you don't have to, it'll do everything for you. $62.25. So you're getting actually charged at a different rate depending on your usage.